Hello, in today's maths tutorial video, we're going to be covering how you can convert from parametric equations to Cartesian equations if there are no trig functions involved, because I'm going to cover that in a separate video. Anyway, what do you need to know in order to be able to do the basics for these sort of things? The first thing is, again, reiterating, if there are no trig functions involved, because if there are, you need a different approach. But if there are no trig functions involved, then the approach is actually quite easy. All you have to do a lot of the time is rearrange one of the two parametric equations to make t the subject of the formula, and then use that to eliminate that t that's appearing in the other formula. And once you've done that, boom, it's only in terms of x and y now, so you've got a Cartesian equation. Brilliant. So, putting that into practice, here's an example. There's an element of tactics to this stuff. You have more than one equation to choose from to rearrange, so therefore choose the one that's going to obviously be easier to rearrange. In this case, it's going to be this one, because there's only a t in one place, whereas to rearrange the other one, it's going to take many more steps. So, if I rearrange this first equation, well, it's not the first equation, it's the one I've highlighted anyway, we can get e to the power of x equals t minus 3, and therefore e to the x plus 3 is equal to t, and there you go. We've now got a ready-made substitution that we can use to eliminate all the t's that we see in that first parametric equation, which therefore means when we substitute that in, we are going to get y equals e to the power of x plus 3 all squared. Note my good use of brackets there to ensure everything I'm replacing t with is being squared just like t was originally. Minus 5 lots of, again, making good use of brackets, e to the x plus 3, because it's 5 lots of all of that, and then adding 2 on the end. And there you go, you do have a Cartesian equation at this stage. Admittedly, a lot of exam questions will require you to simplify it or write it in a certain way. Like, I wouldn't be surprised if this was an exam question. They would be expecting people to multiply out the brackets with the squared there. So therefore, we're going to end up with e to the 2x plus 6e to the x plus 9 minus 5e to the x minus 15 plus 2. And therefore, the final answer would be y equals e to the 2x plus e to the x, and then we have got minus 4. So there you go, that is a Cartesian equation for these parametric equations. Now, for those of you who are just looking to nail the basics so you can get that pass mark you're aiming for, then to be honest, this method I've just shown you will do you for pretty much all the questions that involve converting from parametric to Cartesian that don't involve trig functions. You do still need to know that stuff as well. As I said, separate video on that. But for those of you who are aiming for an A or an A star, one of those really high flying grades, then there's still a few more tricks that I can show you. Worth mentioning, they're not tricks that I'm expecting people to go away and have to practice 50 billion questions on to try and drill these ideas in, but it's just I'm trying to show you them because it's good to be aware that they exist. So the first thing I'm going to point out is, once again, reiterating, just like I did in my quotient rule video, that we don't like leaving final answers that have got fractions within fractions. Sometimes if questions are show that questions, they will be trying to subtly encourage you to avoid the situation anyway, but therefore just be aware, of the tricks you can use in order to do that. So, as usual, the first thing we can do is be tactical, pick one of the equations, rearrange it to make it t equals. Of course, this is going to be the much easier one to do, so therefore I'm going to start by realizing, of course, that t to the power minus 1 means 1 over that thing. So therefore, we could multiply both sides by t, we could divide both sides by y, and there you go. We've got an equation that's t equals, which we can then use to eliminate the t that's appearing in the equation for x equals. So doing that, we've got x equals, it was 5t, it's now going to be 5 lots of either 1 over y or y to the power minus 1, however you want to write it. And then on the bottom, 11 lots of y to the power minus 1, and then plus 6. Now, although I have chosen to write it as y to the power minus 1 rather than 1 over y, it doesn't really matter. But either way, we've got effectively a fraction within a fraction situation, because that y to the power minus 1 means 1 over y. We don't like that. So the way we can deal with that is kind of combining two sort of tricks we've used before. One of which is the fact that if you've got an equation with a fraction with algebra on the denominator, multiply by the denominator to eliminate it. Cool. The thing is, though, we've also got a bigger fraction in this situation, and you can rewrite big fractions, or just fractions in general, by multiplying the top and the bottom by the same thing, or dividing the top and the bottom by the same thing. So therefore, combining those two ideas together, we can get rid of the y to the power of minus 1s by multiplying by y to eliminate the denominator of y that's in the 1 over y part, but then multiplying the top and the bottom of the big equation by y so that we are maintaining the same big fraction that we had before. So therefore, we are going to end up with 5 y to the power minus 1 times by y is just going to be 5 minus 3y, and then 11 plus 6y. And there you go. Now we don't have fractions within fractions, and therefore that's a much nicer answer. After that, it's worth mentioning, technically you could rearrange this equation to make it y equals, and if the question asked me to do that, I would. This question hasn't, so I've got a Cartesian equation, we're done, but just making you aware of that fact. And then another trick to be aware of is it's generally a good idea to avoid introducing square roots with the intention of using that to rearrange or inverse a squared operation. So for this particular example I've got here, it'd be very easy to look at it and just go, oh, you know what, I could just rearrange this equation to make it t equals by basically square rooting both sides. And the problem is that will end up cutting out a part of the graph, because if you use square root to undo a squared, we already know from solving quadratics you will lose solutions if you do that. Of course, the way we get around that normally when we're solving quadratics is we put a plus minus in front, but then we really don't want to be using that as something to plug in, because A, we've got a square root involved now, that looks horrible, and a plus minus, okay, that looks really horrible as well. So yeah, okay, technically the answer could then be rewritten as this, but this looks really, really nasty, so we don't want to write this as an answer. So instead, sometimes you just have to ultimately be willing to play about with the algebra and sort of adapt your approach as you go. So for instance, sure, we before tried to just eliminate all the t's at once by rearranging one of them to make it t equals, and then using that to get rid of all of the t's in one go. That didn't work out, but we can do a halfway approach for that by going, oh, okay, we can't get rid of all the t's doing that, but we can at least notice x has a 9t squared in it, and y is t squared, so we can use that to eliminate the t squared to start with, so then there's less t variables we're trying to remove. So therefore, if I do that, I'm going to end up with x equals 9y minus 5t, and then we can notice, oh, wait a minute, now there's only a t in one place in this equation. Now it's something that would be quite easy to rearrange to the point where we've got a t equals in this equation. And so therefore then I'll be able to then plug it back into another equation again. So for instance, we could divide both sides by minus 1/5. And now I could try and plug that into y equals t squared. So therefore y will equal, not t squared, it will be minus 1/5 x minus 9y all squared, like that. Now it's worth mentioning some people might have chosen to multiply out those brackets with the fifth first, but it doesn't matter. You can use index laws to help you square this out. So therefore it will be minus 1/5 separately squared, and then x minus 9y separately squared. So therefore we'll end up with 1 over 25 lots of x squared minus, if you properly fully multiply it out, the x times by the minus 9y, but that's going to happen twice, so we end up with minus 18xy. You might already start to see why this is so good. It's ending up exactly what we wanted it to be. Minus 9y times by minus 9y is plus 81y squared. Again, that's ending up exactly how we want it to be. And then, of course, because we know what we're heading towards, we don't want that 1 over 25th in front of all that stuff. So therefore, multiply both sides by 25. And there you go. You've identified that the value of the constant a must be 25. And so therefore, I am going to make a point of highlighting that to the examiner, even though this is in reality the equation we're heading towards. So there you go. Either way, I've definitely got all the marks. And again, one final trick I'm going to show you today is, again, to reiterate that you just have to sometimes be willing to play about with the algebra. There will be those situations where you can't just rearrange one of them instantly to be t equals no matter how hard you try. So therefore you might have to start playing about with things to try and get a situation that allows you to eliminate all the variables that are the parametric variables. So for instance, here is an example. You can see both of these equations involve multiple t's in multiple places, and so therefore there's no nice easy way of eliminating the t's instantly anyway. Two main approaches that you could use to help do this question. One of them could be to use a similar approach as a previous example where you accept that you're not going to be able to get rid of all the t's in one go, but you could just get rid of one of the t to the power of whatever parts that you can see. For instance, in this one you could rearrange both equations so that they're 9t to the power minus 2 equals some stuff with t's involved on the other side as well, but at least it would eliminate the 9t to the power minus 2 parts. But the other trick you might want to watch out for that appears in this question is you might notice that one of the equations has the plus 9t to the power minus 2 and the other one has minus 9t to the power minus 2. So what we can do is actually employ a very similar trick that you used to use on simultaneous equations probably way back when you first came across them, which is you can eliminate things that are appearing as plus and minus in a different equation by adding the two equations together. So if we do the x equation plus the y equation, we're going to end up with 4t plus 9t to the power minus 2 plus 2t minus 9t to the power minus 2, which is then not going to get rid of all the t's, but it does at least get rid of that part that's appearing as a plus in one of the equations and a minus in the other equation. And so we've got x plus y equals 6t. And oh my goodness, what have we done? We've ended up creating an equation that can now be rearranged to be t equals. So we've got t is equal to x plus y over 6. So therefore that means I can now continue on and use that to eliminate the t in one of my two equations. I'm going to plug that into, well, let's plug it into the y equals equation. We'll end up with two lots of x plus y over 6 minus 9. It is t to the power minus 2, which means 9 over t squared, so therefore I'm going to write it on the bottom of a fraction. So it's 9 over x plus y over 6 in brackets to the power of 2. And then, oops, forgot to close those brackets, we can then ultimately stop there if we don't need to continue on further depending on what the question's asking us, but this isn't a fully simplified answer. So if we are continuing that on, we'd realise the 2 divided by 6 simplifies to 1/3. So we've got 1/3 lots of x plus y. And then if you square that fraction that's on the bottom of the bigger fraction, you're going to end up with x plus y all squared divided by 36. But again, this is a fraction within a fraction situation, so the thing you might choose to do is then realize that if you're dividing by a fraction, it's the same as multiplying by the reciprocal of that fraction. So 9 times by 36 divided by x plus y all squared, which will end up being 324 over x plus y all squared. Could even then choose to, for the sake of completeness, simplify even more. We could times both sides by 3 to eliminate the 1/3. You could then gather the y that's on the left hand side and the y that's currently a 1/3 y on the right hand side into one big thing. But whatever, it's all just algebra rearrangement. But there you go, those are all the tricks I wanted to show you in this video, but do be aware we also need to know how to convert from parametric to Cartesian if there are trig functions involved. I'm going to have a separate video on that, so do watch that when that is eventually released. Goodbye!